Draeger manufactures 4 different types of sensors. We will review a short definition of each type of sensor, and then later provide a more detailed overview of each sensor and its function. An electrochemical or EC sensor measures the concentration of a target gas by oxidizing or reducing the target gas at an electrode and measuring the resulting electrical current output. These types of sensors are used for detecting oxygen and toxic gases. A catalytic, CADX, or combustible sensor oxidizes a combustible gas and converts the temperature change into an electrical signal. These types of sensors are used for detecting combustible gases. This sensor is also called an LEL sensor. An infrared or IR sensor measures trace gases by determining the absorption of an emitted infrared light source through a certain air sample. These types of sensors are used for detecting carbon dioxide and a wide range of combustible gases. A photoionization detector, or PID, breaks molecules into positive and negative charged ions and measures the electrical charge of these ions on a detector to display the amount of gas or vapor that is present. These types of sensors are used for detecting volatile organic compounds, VOCs, and toxic gases. Let's look at each type of sensor in more detail. Let's first look at electrochemical sensors, as they are among the most common types of sensors used in gas detection monitors. Draeger's electrochemical sensors are different than our competitors' sensors, and this section of the training will discuss these differences and their importance. To help you better understand what is actually happening in the electrochemical sensor, here is an animation to demonstrate the process. The basic principle behind an electrochemical sensor involves at least 2 electrodes, which have contact with each other in 2 ways. First, through a liquid electrolyte, and second, through an external electrical circuit. As gas enters the sensor chamber, a chemical reaction takes place at what is known as the 3-phase zone, where gas, the electrodes, and liquid electrolyte meet. This chemical reaction generates an electrical current, which is measured by the external electrical circuit. A dual electrode sensor does, however, have many drawbacks. For instance, if high concentrations of gas occur, this leads to higher currents in the sensor. This high current can lead to unusable readings, or in the worst case, it can cause the chemical reaction inside the sensor to stop during the measurement process. Unlike some competitors, the Draeger XS and XXS sensors contain a third electrode known as the reference electrode, which does not have a current passing through it. It continuously measures the sensor voltage at the measuring electrode, which can be corrected using the sensor's control enhancement. This produces a considerably improved measuring quality and a longer lifetime. Let's review the process again by looking at this diagram. First, gas needs to pass through the membrane to enter the sensor chamber. This membrane is made of a hydrophobic material that is designed to keep water from getting into the sensor and keep the liquid electrolyte from getting out of the sensor. As we mentioned earlier, there are sensing and counter electrodes inside the electrolyte, where the chemical reaction takes place when target gas enters the sensor. There is also a reference electrode in the electrolyte that provides stability and a reference point for more accurate readings. This electrolyte and electrodes combination has been designed to react as much as possible to the target gas. Once that gas enters the sensor and comes in contact with the sensing electrode and electrolyte, a chemical reaction occurs, generating an electrical current. The current is made up of electrons that leave the sensor through an outside circuit, where it is amplified and measured by the gas monitor. The higher the concentration of gas, the higher the current output will be. Once exposed to fresh air, the chemical reaction to the gas is reversed on the counter electrode, taking the sensor back to its original state. Electrochemical sensors can be categorized as consumptive or non-consumptive, based on the way the sensor is constructed. The material of the electrode in the consumptive sensor is broken down and used to create the chemical reaction necessary for the sensor's function. This process is called oxidization. The speed of the consumption of the electrode is based on the amount of gas that is present. If there is a sudden high concentration of gas, the electrode could be used up rapidly. The sensor would stop working because there is no longer any electrode material available to complete the chemical reaction. This is mostly seen in the oxygen sensors of many of Draeger's competitors, but can also be seen in ammonia sensors. In order to avoid this type of consumptive reaction, Draeger sensors have been designed to function differently. Most of Draeger sensors are designed to be non-consumptive. In these sensors, not only do we use catalytic electrode materials that are not consumed in the chemical reaction, but once the gas dissipates, we also reverse the chemical reaction back to where it was before the gas was introduced. This is done with the counter electrode. The Draeger oxygen sensor is unique in that it does not contain a lead-based electrode that gets consumed with exposure to normal air. The oxygen sensors manufactured by some of Draeger's competitors are made with a lead-based electrode, and they begin to degrade immediately after the first use. Draeger's electrochemical sensors can be found in your pack XM 2500, 5000, 5600, and 7000 instruments. The next type of sensor that we will talk about is the catalytic sensor. This sensor is used for those applications that need to detect and measure combustible gases. The catalytic sensor is the most common type of sensor for combustible gas measurements. To help you better understand what is actually happening in the catalytic sensor, here is an animation to demonstrate the process. The gas to be measured enters the sensor chamber through the flame arrestor. The flame arrestor prevents the energy from the oxidation process from getting back out to the atmosphere. The element's heated catalyst, which is about 500 degrees Celsius, facilitates the reaction between the gas entering the sensor and oxygen in the air. This reaction causes the element to heat up to even higher temperatures. The increase in heat causes the electrical resistance of the element to change. This change of resistance is what is measured to provide the reading on the display of the gas monitor. Just like with the electrochemical sensor, one of the sensor elements is used only to compensate for changes in environmental conditions. The higher the level of gas entering the sensor chamber, the higher the temperature of the measurement element, which means a higher reading on the display. As mentioned before, for proper operation, a catalytic sensor needs oxygen. If the oxygen level drops too low, the gas will not burn effectively, and this will give lower than actual readings on the display of the monitor. With Draeger monitors, if the O2 concentration drops below about 8% by volume, the reading for the combustible sensor will be blanked out. Once the O2 levels come back above 8%, the combustible reading will again be displayed. Let's review the process again by looking at this diagram. As you can see, there is a flame arrestor screen that allows the gas to enter the sensor chamber, but does not allow a flame that may be generated by the reaction to escape out of the sensor. There are also two coiled platinum elements called the detector element and the compensator element. The detector element is coated with a catalyst, and the compensator element does not have the catalyst on it. Both elements have voltage applied to them at the same amount at the same resistance. To explain how this reaction works, we will use methane as the target gas. Methane has a 5% by volume LEL, which, as explained before, means that it becomes flammable when 5% of the air is made up of methane. In order to meet the OSHA requirements, the sensor is calibrated so that it goes into alarm before it would reach the 100% LEL mark. So it may seem like we have an impassable problem. We need the methane to burn in order to measure the change in resistance due to the detector element heating up. How can this be done if we don't want the sensor to see air that has a flammable methane concentration? This is where the catalyst comes into the equation. The catalyst causes oxidization to occur. In simple terms, the catalyst on the detector element groups the oxygen in one area of the sensor. It allows the methane molecules to find the oxygen molecules easier, enabling it to burn at a lower percent by volume. The combustion occurs, and the temperature increases, which in turn increases the electrical resistance. The detector element's new resistance is compared to the compensator element's resistance, and the difference in resistance is measured. This information is used to calculate the concentration of methane. The monitor will take this reading and go into alarm if the environment has become hazardous. This type of sensor can be found in your XAM 2500, 5000, and 7000 instruments. The next type of sensor that